This is a very important lecture. So here we are going to study lateral stability augmentation system. First, we will start with the open loop system behavior, how the system is going to respond without any control. Then we will use the state feedback control concept, what you have done before. Then we'll have the control authority, how we can come up the Z, what we have discussed in the last lecture, using the control authority concept, how we can come up the closed loop system response for multi-input controls. So first, let me discuss the problem, what you're going to do. The problem is, this is very, very important. Here, I'm going to do a lot of stuff. We'll look the system from the beginning, how we'll go step by step, design the control. And the lateral stability, the lateral state space equations are defined as, so we are going to consider the full lateral dynamics, delta beta dot, delta p dot, delta r dot, and delta p dot. And we have the system matrix minus 0.05, minus 0.003, minus 0.98, and 0.2. These are the stability derivative terms in the system matrix. Minus 1, minus 0.75, 1, 0, 0.3, minus 0.3, minus 0.15, 0, 0, 1, 0, 0. So this matrix varies for the different flight regime for the different aircraft. So this can be for the particular aircraft, delta beta, delta p, delta r, and delta p. And we have the control matrix, which is 0, 0, 1.7, minus 0.2, 0.3, minus 0.6, 0, 0. And we have the control inputs, delta del A, delta del. So we have the aileron and rudder deflections are there to control the body orientation. And here, the question is, this aircraft is found to have 4 handling qualities. Why it is 4 handling qualities? We will discuss these qualities in lateral, directional, design a stability augmentation system such that the desired eigen values for lateral characteristic damping ratio for roll minus 5.5. This is roll mode. Okay, this is a mistake. So this be is the eigenvalues, and a spiral, as you know, for in the lateral direction of motion, we are having three different approximation: roll, spiral, and Dutch roll. These things we have already discussed in our first course, Introduction to Aircraft Control System. A spiral 0.05. This is also called spiral mode. And is Dutch roll 0.35 plus minus 1.5. This is called Dutch roll mode. So based on the roots, we can define the different mode. So we have to design the control stability augmentation system for this particular aircraft. So let's move. First, we have to check whether the overall system is controllable or not. So for that, we can, in the MATLAB command, we can find the P matrix, the controllability test matrix, CTRB, A, B, we can do, and we can find rank equal to or equal to rank P, and if we enter the MATLAB command, the R is found to be 4, means system is controllable. So we can control all the states in the system. All states are affected by controlling field. Now we'll find the open loop poles of this system, whether the system is stable or not. So for that, we can use the system stability, I think, right? System stability, we can say. So for this, we have to use the command omega n, natural frequency, zeta for the damping ratio, and poles. So this will give you the open loop system characteristic. Then A, and if you enter, we have natural frequency vector. So since we are having 4 states, so 4 different values will be there. 88, 0.88, and 0.03. This radian per second. And zeta, the damping ratio, found to be 1, 0.004, 0.004, and minus 1. And poles found to be minus 0.9821 and minus 0.0035 plus minus 0.885 and 0.039. If you notice carefully, in the poles of this open loop system, one pole in the right hand side, and this causes the system is unstable. In other words, if you can say the lateral handling quality is poor. So you can write for this condition, the lateral handling quality is 4 and the system is unstable, right? So now we can we are, if you notice in the last few lectures, we are talking about unstable system, unstable. So let's look the response with this open loop system. If there's no control in the system, how we can study the system characteristic over time. So here we have the plot for this. So if you notice in the MATLAB code, so here you can see that the system is unstable. So it is, though it is bounded, but it is actually oscillating. The system response is oscillating over time. It is not fixed to some constant value. So we can say here, if you, one thing I have to say also here. So here the initial conditions are very important. These are the initial conditions we assume 0, 0, 0.01 and high gradient. Right. So here system is unstable because one of the pole of the system found to be in the right hand side. Now we'll design the control and we'll see how this responses goes to 0 over time. The initial condition will be assumed to be same, and how the control going to mitigate these oscillations over time. So for that, we have to design the control. So let's find the control gain matrix. So already we are having the poles of the system. So these are poles are given in the problem. So here we can form, we can write here control design. It will help us to mitigate these oscillations. So now we have the digit folds given in the problem. So from that, we can form the V matrix of the vector minus 5.5, 0.05, minus 0.35, plus minus 1.55 and minus 0.35 minus 1.55. So this is the digit poles. So now we can use the place command to find the control gain parameters. A place, this is already you have done before. How to find the gain of the system, control gain of this controller. So place A, B, and P. Also, we have done numerically how we can solve the equation to find K place. So we are not doing this. This already have done. K place provide the control gain parameters in terms of matrix 0.22, 3, 0.29, minus 0.12. And since there is two controls, so the control gain parameter in a matrix form 2 minus 0.68, 0.03. Now, from this, we can find the closed loop matrix or the augmented matrix, control matrix. So the augmented, or we can controlled matrix, we can say ACL equal to A minus BK. So here we can use the command. So here actually I'm not going to discuss on this because the MATLAB code simply. So the MATLAB code of the closed loop system, we can found to be, the code is given on things written here. So here is the response. So come to the next page. So here the step by step given. This is the V matrix, this is K place, and this is the system in state space form. And if you write initial command, it will give you the values of the states, and if you plot, this is our response. Now, so whatever things we have done here, this is in the code, and the plotting the response of the system, they are the same function we use here. If you notice carefully, the beta, delta P, delta R over time are stable. The oscillations are dies out and goes to the stable condition. But the problem is delta phi. Delta phi, if you notice carefully, though in 15-20 seconds it was bounded, but if you plot for a longer time, it is actually increasing. So it means this is basically the handling quality for the delta phi not good. So here we can use the control authority methods, what you have done in the last lecture. So this method will be using. So this part we have done. So now we are going to do what we have done in the last lecture, the control authority design concept, which will help us to control this dynamic state. So here we are defining, let us define, you can try this code, you can try in your MATLAB command window, and you can see the response. And I request you please do it so that you can understand how you can write the code. This is nothing but autopilot. We are designing the autopilot for the system, right? So let us define control authority as this del A aileron 2.5 times the radar deflection. So to control the roll, we are using this condition. Okay. So here, from this, we can find del R divided by del A equal to 1 up 2.5, 0.4. And we are defining Z1 to be 1, and G2 we can define as del R del A equal to 0.4. So if you want to write in MATLAB Z equal to 1, 0.4 transpose, and B star, what we have done in the last lecture, B into C. So this will give you the B star matrix. So if you want to write in MATLAB code, B star, the gain matrix, control matrix of the closed loop system is based on these conditions. We can write place command, we can use A, B star, or instead of that we can write B, if you add B star here, we can write like this, B star. The digit eigenvalues assume to be same, and the output of this command A star is found to be 13, 3.6, 11.5, minus 0.27. It's found. So here actually it is not matrix anymore, it is a vector instead of that. And you can use the same command. You can find sys cl2 second system, 2 for second system. Cl is the closed loop system. SS you can use this command A minus B star into A star zeros. This is the closed loop system. We can put it as 0, 4, 1, C and D. The same C and D matrix we are using here. And you can use the command ytx equal to initial sys cl2 this system, and we need to have initial condition. Same initial condition we are assuming, and we'll have list of data, and this is the data, and you can plot them, right? So the response is found to be, this is the response of the system. So if you notice carefully here, we can see that now the problem what you had in the previous case, now it is stable. It is going to 0 over time. At 20 seconds, all states are converged to zeros. So now system is control. So using this control authority concept, now we are able to get our desired response. So this is very, very important, this example. So in this example, we studied how we can study the open loop system. And also, if you want to design, to mitigate the oscillation in the response, we come up the state feedback control. And also, we found that one of the state was not going to 0. It is increasing over time, the value of magnitude of the state. And if you use the control authority function, what we have done here, using that, we can achieve our desired goal. So now, this is how we can design the handling quality. You can improve the handling qualities of the aircraft system. So it is fulfill our objectives. I hope these codes are very important for you. For the different cases we need the code. This is for the open loop, there is no control. So that's why the system having sustained oscillation in the response. And here we have designed the control, but one of the state was not controlled. And then we apply the control authority concept. And based on that, the redefined control algorithm can able to improve the handling qualities of the system. So let's stop it here. This is the last, this is one more lecture we'll have, how to design the altitude hold control of the aircraft. And after that, we'll move to nonlinear control concepts. Let's stop it here. Thank you.